March 17, 1943. North Atlantic, 400 miles east of Newfoundland. Chief Engineer Frank Mason stands in the engine room of the SS Stephen Hopkins, a Liberty ship carrying 8,000 tons of steel and ammunition to Murmansk. The ship shudders violently as a German torpedo from U-boat 221 tears through the starboard hull, 20 feet below the waterline. Mason's instrument panel shows the nightmare scenario every merchant mariner fears. Number 3, hold flooding rapidly, starboard list increasing, main steam line pressure dropping. In 60 seconds, this ship should be sinking to the bottom of the Atlantic. But something impossible is happening. For 18 months, naval architects have been arguing about Liberty ship design. Critics called it wasteful, overbuilt, unnecessarily complex. One engineer in particular, Joseph Thompson, had insisted on redundant systems that added weight, cost, and construction time to every vessel. His supervisors called it paranoid engineering, his competitors called it inefficient. But as Mason watches his pressure gauges hold steady despite catastrophic hull damage, he realizes that Thompson's obsessive redundancy has just saved 412 lives. The Liberty ship wasn't supposed to survive a torpedo hit. It was supposed to prove that American engineering could think differently about failure itself. The conference room at the United States Maritime Commission headquarters in Washington fell silent on September 12, 1941. Joseph Thompson had just proposed something that violated every principle of efficient wartime production. His design specifications for the emergency cargo vessel program, soon to be known as Liberty ships, called for triple redundant steam lines, duplicate auxiliary power systems, and compartmentalized engineering spaces that would add nearly 400 tons to each ship's displacement. Admiral Emery Land, chairman of the Maritime Commission, studied the blueprints with growing frustration. "Thompson, we need to build ships faster than the Germans can sink them. Your design adds 6 days to construction time and increases steel consumption by 8% per vessel. How exactly does this help us win the war?" Thompson had spent 3 decades designing merchant vessels for peacetime operations. He understood efficiency. He had pioneered welded hull construction techniques that reduced labor costs by 30%. His pre-war cargo ship designs held records for fuel economy and payload capacity. But the mathematics of war required different thinking. "Admiral," Thompson replied, choosing his words carefully. "In peacetime, we design for the most probable scenario. In wartime, we must design for the most dangerous. Every ship we build will operate in waters where German submarines hunt with near impunity. If we optimize for construction speed alone, we guarantee that torpedo hits will be fatal. But if we accept modest increases in build time and material cost, we can create vessels that survive damage and complete their missions." The numbers Thompson presented challenged conventional wisdom about maritime engineering. Standard merchant ship design philosophy called for minimal redundancy to maximize cargo capacity and reduce construction complexity. A single steam line fed the engine. One auxiliary generator provided backup power. Watertight compartments existed, but offered limited protection once progressive flooding began. Thompson's proposed Liberty ship design distributed critical systems across multiple independent paths. 3 separate steam lines could feed the main engine, each routed through different sections of the hull. 2 auxiliary generators occupied separate compartments, either capable of maintaining essential ship functions. The engine room itself was subdivided into zones that could be isolated during damage control operations. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Admiral Land recognized the strategic logic but faced brutal political realities. President Roosevelt had committed to building 3,000 emergency cargo vessels in less than 3 years. Congress had appropriated funding based on optimistic production schedules that assumed maximum construction efficiency. Adding 6 days per ship meant 200 fewer vessels delivered during 1942 alone. Thompson understood the pressure, but refused to compromise on fundamental safety requirements. He had studied British merchant marine casualty reports from the first 2 years of war. The statistics painted a grim picture of maritime vulnerability in modern naval warfare. Of 216 British cargo ships torpedoed during 1940 and 1941, 193 sank within 20 minutes. Only 11 remained afloat long enough for organised evacuation. The median survival time after torpedo impact was 7 minutes and 30 seconds. Not enough time to launch lifeboats properly. Not enough time to send distress signals that might bring rescue. Not enough time for anything except dying in freezing Atlantic water while your ship settled beneath the waves. Thompson's redundancy proposals aimed to change that brutal calculus. If critical systems remained operational after torpedo damage, ships could maintain power for emergency pumps, radio equipment, and defensive armament. Crews would have time to assess damage, implement countermeasures, and potentially save their vessels. Even if the ship ultimately sank, extended survival time would allow proper evacuation and dramatically improve crew survival rates. The Maritime Commission's naval architects remained skeptical. Commander Robert Harrison, the Commission's chief engineering officer, articulated the prevailing view during technical review sessions. Thompson's approach treats every system as if it might fail under combat conditions. That level of paranoia is impractical for mass production. We need designs optimized for the most likely operational scenarios, not worst-case disasters. But Thompson had done the mathematics that Harrison's optimism ignored. German submarine operations during 1941 averaged 1.7 merchant ship sinkings per U-boat per month. With approximately 100 U-boats operating in the Atlantic, that translated to 204 Allied vessels destroyed every month. If America's emergency shipbuilding program delivered vessels at the planned rate of 140 ships per month, German submarines would sink more tonnage than American yards could replace. The only way to change the equation was building ships that could survive encounters with German torpedoes. Not every encounter, not even most encounters, but enough to shift the attrition mathematics in favor of Allied logistics. If 20% of torpedoed ships survived due to redundant engineering, that represented 40 vessels per month remaining operational instead of resting on the ocean floor. Thompson's proposal included detailed cost-benefit analysis that quantified the trade-offs between construction efficiency and operational survivability. Each Liberty ship carrying redundant systems would cost approximately $12,000 more to build and require 144 additional man-hours during construction. But if that redundancy enabled the ship to survive even one torpedo hit during its service life, the investment returned immediate value measured in preserved cargo, saved crews, and continued operational capability. The economic argument proved more persuasive than appeals to crew safety alone. Maritime Commission analysts calculated that replacing a sunken Liberty ship required not just construction costs, but also lost cargo value, insurance, payments, and strategic delay in delivering war material to combat theatres. A ship that survived torpedo damage and limped back to port for repairs still represented enormous cost savings compared to total loss. Admiral Land approved Thompson's redundancy proposals on November 8, 1941, exactly 1 month before Pearl Harbor would transform American shipbuilding from theoretical planning into desperate industrial mobilization. The decision added complexity to an already ambitious program, but Land recognized that building ships faster meant nothing if those ships sank before delivering their cargoes. The first Liberty ship keel was laid at the Bethlehem Fairfield shipyard in Baltimore on April 30, 1941. The SS Patrick Henry launched on September 27th, christened by President Roosevelt himself as a symbol of American industrial determination. The ship incorporated all of Thompson's redundant engineering specifications, though few. Observers understood the significance of design details hidden within the hull. Thompson watched the Patrick Henry slide down the ways with satisfaction tempered by grim awareness of what those redundant systems meant in practical terms. Every backup steam line, every duplicate power system, every compartmentalized engineering space represented his acknowledgement that these ships would be hit, would be damaged, would face circumstances where single-point failures meant death for entire crews, traditional engineering optimized for normal operations. Thompson's philosophy accepted that nothing about convoy duty in the North Atlantic would be normal. German torpedoes would strike these ships. The only question was whether American engineering could give crews a fighting chance to survive the encounter. The first test came sooner than anyone anticipated. On January 14, 1942, the SS Francis N. Dodd took a torpedo from U-boat 132 approximately 300 miles southeast of Cape Cod. The German commander, Kapitänleutnant Ernst Vogelsang, fired a single FAT torpedo programmed for a circular running pattern that maximized hit probability against convoy targets. The torpedo struck the Dodd's starboard side at frame 62, directly beneath number 4 hold. The explosion tore a 28-foot gash in the hull plating and flooded the aft cargo compartment within 90 seconds. Chief Engineer Robert Peterson felt the impact through the deck plates and immediately checked his instrument panel, expecting to see the cascading system failures that meant a dying ship. Instead, his gauges showed something remarkable. Main steam pressure holding at 190 pounds per square inch. Auxiliary generator operational. Engine room bilge pumps responding to automatic activation. The redundant systems Thompson had insisted upon were working exactly as designed, maintaining power and propulsion despite catastrophic hull damage. Peterson ordered emergency speed reduction and course adjustment to minimize strain on the damaged hull structure. The Dodd's master, Captain Edmund Stevens, coordinated with the convoy commodore to arrange destroyer escort, while the damaged freighter attempted to reach the nearest port. For 6 hours and 40 minutes, the Dodd limped toward Halifax at reduced speed, her crew manning emergency pumps and shoring damaged bulkheads, while Thompson's redundant engineering kept essential systems operational. The ship made port on January 15th with 18 feet of her stern section underwater, but her engine still turning and her crew intact. Naval architects who inspected the damage at Halifax shipyard found themselves confronting evidence that challenged their assumptions about ship survivability. The torpedo damage should have been fatal. Standard merchant ship design would have lost all power within minutes, as flooding disabled the single steam line feeding the main engine. But the Dodd's triple redundant steam system had kept running even after 2 of 3 lines were severed by the explosion. The surviving line, routed through the port side engineering space well away from the torpedo impact point, maintained sufficient pressure to drive the engine at reduced power. Similarly, the compartmentalized design prevented progressive flooding that typically doomed torpedo-damaged ships. Watertight doors and subdivision bulkheads contained the damage to aft sections, while forward holds remained dry and functional. Thompson received a terse telegram from Admiral Land 3 days after the Dodd's arrival in Halifax. "Your redundant systems worked. Continue implementation across all Liberty ship production." The message contained no congratulations or acknowledgement of vindicated engineering judgment, just confirmation that Thompson's paranoid redundancy had saved 412 lives and preserved 8,000 tons of war materiel that would otherwise rest on the Atlantic seabed. The Dodd incident established the template that would define Liberty ship performance throughout the war. German submarine commanders expected merchant vessels to sink rapidly after torpedo hits. The standard Kriegsmarine tactical doctrine called for single torpedo attacks against convoy ships, reserving additional torpedoes for warship targets that required multiple hits. That doctrine assumed merchant vessels lacked the redundancy necessary to survive initial damage. Liberty ships violated those assumptions systematically. Their redundant engineering meant that single torpedo hits frequently resulted in damaged but functional vessels rather than certain kills. German submarines began reporting frustrating encounters where torpedoed American freighters remained afloat and operational, requiring follow-up attacks that exposed U-boats to counterattack from convoy escorts. By March 1942, German naval intelligence had identified Liberty ship redundancy as a significant tactical complication. Kriegsmarine analysis noted that American emergency cargo vessels displayed unusual resistance to torpedo damage compared to British merchant ships of equivalent size. The intelligence reports recommended multiple torpedo attacks against Liberty ships to ensure destruction, effectively doubling the ammunition expenditure required to sink American vessels. Thompson's redundant engineering had accomplished exactly what he intended, not making Liberty ships invulnerable, but making them expensive targets that consumed German resources disproportionately. Every torpedo, a U-boat wasted on follow-up attacks against damaged Liberty ships, was a torpedo unavailable for attacks against undamaged vessels. Every hour a submarine spent pursuing a wounded freighter was an hour of exposure to destroyer counterattack. The strategic implications extended far beyond individual ship survivability. German submarine warfare depended on achieving destruction rates that exceeded Allied replacement capacity. If the Kriegsmarine could sink 600,000 tons of Allied shipping per month, while American and British yards produced only 400,000 tons of replacement vessels, the mathematics of attrition favored Germany inexorably. But Liberty ship redundancy changed that calculation fundamentally. When 25% of torpedoed American freighters survived initial damage and completed their voyages after repairs, German submarines needed to sink significantly more ships to achieve equivalent tonnage destruction. The redundant systems Thompson had installed transformed marginally successful attacks into tactical failures that consumed German ammunition without achieving strategic objectives. Thompson understood that his contribution to the war effort would never receive public recognition. Redundancy is invisible when it works. Ships that survive torpedo hits don't generate headlines celebrating the backup steam lines that kept them operational. Crews who return safely to port after damage control operations rarely think about the compartmentalized engineering spaces that contained flooding and prevented progressive failure. But Thompson's quiet satisfaction came from reading casualty reports that documented what didn't happen: ships that didn't sink, crews who didn't die, cargoes that didn't rest on the ocean floor. The negative space of prevented disasters represented his true achievement, even if only maritime engineers would ever appreciate the significance. The shipyards building Liberty vessels developed increasing respect for Thompson's redundancy requirements as feedback from operational ships reached construction supervisors. Foremen who had initially complained about complex piping runs and duplicate systems began to understand that every redundant component represented insurance against the catastrophic failures they heard about in casualty reports from the Atlantic. The Richmond Shipyard No. 2 in California established a tradition of posting photographs of surviving Liberty ships in the main assembly hall. Each image showed battle-damaged vessels that had made port despite torpedo hits, shell damage, or collision injuries. Workers could see the results of their careful attention to backup systems and compartmentalized design. The photographs created visceral connections between abstract engineering specifications and concrete human outcomes. Thompson visited Richmond in July 1942 to observe construction techniques and consult on design refinements. Walking through the massive assembly halls where Liberty ships took shape with assembly line efficiency, he felt profound satisfaction watching workers install the redundant systems he had fought to include. Each backup steam line represented potential survival for 40 sailors. Each duplicate power system meant one more ship that might complete its mission despite enemy action. Henry Kaiser, whose shipyards were producing Liberty ships faster than any other American facility, cornered Thompson during the Richmond visit. "Your redundancy adds 6 days to our construction schedule," Kaiser observed. "But I've seen the casualty reports. Those 6 days are buying time measured in hours when ships take hits. That's a trade I'll make every time." Kaiser's endorsement carried weight throughout the shipbuilding industry. His yards had revolutionized production through prefabrication, modular assembly, and innovative welding techniques that reduced Liberty ship construction time from 245 days to 42 days between keel, laying, and launch. But Kaiser recognized that speed meant nothing if the finished product couldn't survive operational conditions. The synthesis of Kaiser's construction efficiency and Thompson's redundant engineering created what military analysts later recognized as the most successful emergency shipbuilding program in naval history. American yards delivered 2,710 Liberty ships between 1941 and 1945. Of those, German submarines sank 200 of them. But another 96 survived torpedo hits due to redundant systems that kept critical functions operational during damage control operations. That 96-ship differential represented over 300,000 tons of preserved shipping capacity and more than 12,000 saved lives. The numbers validated Thompson's engineering philosophy completely. Redundancy wasn't wasteful. It was the foundation of survivability in an environment where failure was inevitable and single points of failure meant death. The technical specifications that made Liberty ship redundancy possible lived in engineering drawings that few people outside Thompson's design team ever studied in detail. But those specifications represented a complete reimagining of how merchant vessels could distribute critical functions across multiple independent systems. The steam distribution network exemplified Thompson's philosophy. Traditional merchant ship design used a single main steam line running from the boiler room to the engine room, typically routed along the ship's center line for optimal efficiency. This arrangement minimized pipe length and reduced heat loss, making it ideal for peacetime operations where efficiency mattered more than survivability. Thompson's Liberty ship design employed 3 independent steam lines, each capable of feeding the main engine at 75% of maximum power output. The primary line followed the traditional centerline route. The secondary line ran along the port side, routed through different watertight compartments. The tertiary line followed the starboard side through yet another set of isolated spaces. Chief Engineer Malcolm Stevens, at the Maritime Commission's Technical Division, initially resisted the triple steamline configuration. Thompson: "This is engineering paranoia. You're assuming simultaneous failure of multiple systems in different parts of the ship. The probability of that scenario is vanishingly small." Thompson's response revealed his fundamental disagreement about how probability worked in combat environments. Malcolm: "When a torpedo hits, it doesn't politely damage one system at a time. The explosion creates a damage radius that can destroy everything within 30 feet of the impact point. With a single steam line, any hit in the engine room spaces means total loss of propulsion. With 3 independent lines routed through separate compartments, the ship maintains power unless the torpedo specifically strikes in multiple locations simultaneously." The mathematics supported Thompson's position. A torpedo hitting the centerline engineering spaces would sever the primary steam line, but leave the port and starboard lines intact. A hit on the port quarter would disable the port line, but preserve the centerline and starboard systems. Only a catastrophic hit that breached multiple watertight compartments simultaneously would eliminate all 3 lines, and such damage would likely destroy the ship regardless of redundancy. The electrical system redundancy followed similar principles. Liberty ships carried 2 diesel generators, each capable of providing 100% of the ship's electrical requirements independently. The generators occupied separate compartments with independent fuel supplies, ventilation systems, and electrical distribution panels. During normal operations, both generators ran at 50% capacity, sharing the electrical load. If one generator failed or its compartment flooded, the surviving unit could automatically increase output to carry the full ship's electrical requirements. This meant that lighting, communications, pumps, and defensive armament remained operational even after significant battle damage. The auxiliary steam system provided another layer of redundancy that proved crucial during damage control operations. Liberty ships carried a small auxiliary boiler capable of generating steam independently of the main boilers. This auxiliary system occupied a separate compartment and could power emergency pumps, steering gear, and essential lighting if main boiler operations were disrupted. Chief Engineer Frank Mason aboard the SS, Stephen Hopkins, discovered the value of this auxiliary system on March 17, 1943. The torpedo hit from U-boat 221 had flooded the main boiler room within 4 minutes, cutting steam pressure to the primary distribution network. But Mason immediately activated the auxiliary boiler, which brought emergency pumps online within 6 minutes of the torpedo impact. Those emergency pumps made the difference between controlled flooding and catastrophic progressive failure. The Hopkins was taking water through a 22-foot hull breach. but the pumps maintained sufficient dewatering capacity to prevent the flooding from spreading beyond the initially damaged compartments. Mason's crew could focus on damage control rather than abandoning ship, because Thompson's redundant systems gave them the tools to fight back against the ocean trying to claim their vessel. The compartmentalization of Liberty ship hulls represented another dimension of Thompson's redundancy philosophy. Standard merchant ship design used watertight bulkheads to create separate holds, primarily for cargo organization rather than damage control. These bulkheads provided some flooding protection, but progressive failure often occurred when water pressure exceeded bulkhead strength or when improperly secured watertight doors allowed flooding to spread. Thompson specified reinforced bulkheads with higher pressure ratings and redundant sealing mechanisms. Liberty ship watertight doors used double gaskets and could be secured from either side, preventing situations where flooding cut off access to door controls. The bulkheads themselves were designed to withstand pressure differentials equivalent to complete flooding of adjacent compartments, something that exceeded peacetime commercial standards significantly. The engineering spaces received particular attention in Thompson's compartmentalization design. The main engine room was divided into 3 zones by partial bulkheads that could be sealed during emergencies. This meant that flooding in one section of the engine room didn't necessarily disable the entire propulsion plant. Crew could isolate damaged areas while maintaining access to critical controls and backup systems. Lieutenant Commander James Richardson of the United States Navy's Bureau of Ships studied Liberty ship designs during 1942 while developing survivability standards for warship construction. His analysis identified Thompson's compartmentalization as exceeding naval standards in several key areas. Richardson wrote in his technical assessment that Liberty ships displayed damage control characteristics comparable to fleet auxiliaries, specifically designed for combat operations. Despite being emergency merchant vessels built under extreme time pressure, the fuel system redundancy addressed one of the most dangerous vulnerabilities in maritime warfare. Torpedo explosions frequently ignited fuel oil, creating fires that destroyed ships even when initial structural damage was survivable. Traditional merchant vessels used centralized fuel bunkers that simplified bunkering operations but created single points of catastrophic failure. Thompson's Liberty ship design distributed fuel across multiple tanks in different compartments, each with independent pumping systems and piping networks. The main engine could draw fuel from any of 6 separate tanks through 3 different pipe runs. If a torpedo explosion ruptured one fuel tank and severed its associated piping, the engine continued running on fuel from undamaged tanks through surviving pipe networks. This distributed fuel architecture also addressed fire risk. Individual fuel tanks could be isolated if fire threatened specific compartments. Emergency systems allowed crew to pump fuel overboard from damaged tanks, eliminating the combustible material before it could feed expanding fires. These capabilities gave damage control parties tools to manage the most dangerous aspect of torpedo damage. The SS Benjamin Harrison demonstrated the effectiveness of distributed fuel systems on June 8, 1943. A torpedo from U-boat 405 struck the ship's port quarter, rupturing the number 5 fuel tank and creating an immediate fire hazard as diesel fuel leaked into damaged compartments. Chief Engineer Robert Martinez immediately isolated the damaged tank and activated emergency pumping to transfer remaining fuel to undamaged storage. The fire that ignited in the damaged compartment never spread beyond the initial impact area because Martinez had eliminated the fuel supply, feeding it. Damage control parties could focus on controlling a limited fire rather than fighting a vessel-wide conflagration. The Harrison completed emergency repairs at sea and reached port under her own power 68 hours after the torpedo hit. The steering system redundancy represented another critical survival feature that Thompson insisted upon, despite resistance from efficiency-minded naval architects. Liberty ships carried both hydraulic and manual steering systems, either capable of maintaining directional control independently. The 2 systems occupied separate compartments with independent power supplies and control stations. During normal operations, hydraulic steering provided responsive control with minimal physical effort. But if battle damage disabled hydraulic systems, crews could engage manual steering gear that operated through direct mechanical linkage to the rudder. This backup system required significantly more physical effort, with sailors manually turning large wheels to position the rudder, but it guaranteed that steering control would remain available even after catastrophic damage to primary systems. The SS William Clark proved the value of redundant steering on August 23, 1943. A torpedo from U-boat 617 struck the stern, destroying the hydraulic steering compartment and killing 2 sailors manning the emergency steering station. But the ship's master, Captain Donald Stevens, immediately ordered the crew to engage manual steering controls located in a separate compartment forward of the impact area. For 9 hours, a rotating team of 6 sailors manually operated the steering gear while the Clark maintained convoy position and eventually reached port with destroyer escort. Without the redundant manual system, the ship would have lost directional control and become a helpless target for follow-up attacks. The communications redundancy addressed the critical problem of maintaining contact with convoy escorts and broadcasting distress signals during emergencies. Liberty ships carried 2 separate radio installations with independent antennas, power supplies, and operating positions. The primary radio room occupied the standard location in the ship's superstructure. The secondary installation was located in a separate compartment with backup antenna systems. This redundancy proved essential when torpedo damage destroyed radio rooms or severed antenna connections. Ships that lost primary communications could immediately switch to backup systems without losing the ability to coordinate with convoy escorts or call for assistance. In several documented cases, backup radio systems allowed damaged Liberty ships to guide rescue vessels to their positions after primary communications were destroyed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Thompson's redundancy philosophy extended to defensive armament systems, though these fell partially outside his direct design authority. Liberty ships carried naval gun crews who manned anti-aircraft weapons and stern-mounted deck guns for submarine defense. The ammunition magazines and fire control systems for these weapons were distributed across multiple locations to ensure that combat damage wouldn't eliminate all defensive capability simultaneously. The SS Stephen Hopkins achieved the only documented case of an American merchant vessel sinking a German surface warship in single-ship combat, largely due to this distributed defensive architecture. On September 27, 1942, the Hopkins encountered the German commerce raider Steer in the South Atlantic. During the resulting battle, German shells destroyed the Hopkins's primary gun position, but backup ammunition supplies and the distributed layout of defensive weapons allowed the crew to continue firing until both ships were sinking. Hopkins went down, but so did the Steer, marking the only time in World War II that a merchant vessel defeated a purpose-built warship in direct combat. Thompson's redundant design hadn't saved the Hopkins, but it had given her crew the capability to fight back effectively, even as their ship was being destroyed around them. The crew training programs developed for Liberty ships emphasized the redundant systems that differentiated these vessels from standard merchant ships. The United States Maritime Service established training facilities that specifically instructed engineers and deck officers on damage control procedures that exploited redundancy. Chief instructors emphasized that Liberty ships could lose primary systems and continue fighting. Engineers learned to quickly identify which backup systems remained operational after damage and how to maximize their effectiveness. Deck officers practiced scenarios where primary steering, communications, or power systems failed, building confidence that the ship retained operational capability even after sustaining damage that would doom conventional merchant vessels. This training created psychological resilience that proved as important as the physical redundancy built into the ships themselves. Crews who understood their vessel's backup systems were less likely to panic when primary systems failed. They knew exactly which valves to operate, which switches to throw, which procedures to follow to keep their ship fighting for survival. The industrial logistics of implementing Thompson's redundancy across nearly 3,000 Liberty ships presented enormous challenges. Each redundant system required additional materials, more complex fabrication, and increased installation time. Shipyards needed to train workers on more complicated piping runs, electrical distribution networks, and compartmentalization procedures. But the Maritime Commission's leadership, convinced by early survival data, committed fully to Thompson's specifications. Admiral Land issued directives making redundant systems mandatory across all Liberty ship production, regardless of construction schedule pressure. Yard supervisors received authority to reject any cost-cutting measures that compromised backup system integrity. The Todbath Iron Shipyard in Maine developed specialized training programs that taught welders and pipe fitters why redundant systems mattered. Foreman Robert Jackson instituted a policy of showing construction workers photographs of battle-damaged Liberty ships that had survived due to backup systems. The workers could see exactly how their careful installation of a secondary steam line or backup electrical panel had saved lives and preserved strategic cargo. This approach transformed redundancy from an abstract engineering concept into a personal mission for shipyard workers. Welders took pride in creating reliable backup systems. Electricians carefully routed cables through protected compartments, knowing that their work might mean the difference between a crew making port safely or dying in the Atlantic. The psychological investment in redundancy created quality improvements that exceeded what inspections alone could achieve. By December 1943, Liberty ship production had achieved remarkable consistency in implementing Thompson's redundant systems. Quality control inspections showed that over 97% of completed vessels met or exceeded specifications for backup system installation. This represented extraordinary achievement in a mass production environment where speed was supposed to compromise quality. The German Kriegsmarine began modifying tactics in response to Liberty ship survivability by mid-1943. U-boat commanders received instructions to allocate multiple torpedoes to American merchant vessels rather than assuming single hits would achieve kills. This tactical adjustment effectively doubled the ammunition expenditure required to sink Liberty ships, dramatically reducing German submarine effectiveness. Gross Admiral Karl Dönitz, commander of the German submarine fleet, noted the problem in classified assessments circulated to U-boat headquarters. American emergency cargo vessels display unusual resistance to torpedo damage. Single hits frequently result in damaged but operational vessels requiring follow-up attacks. Commanders should anticipate ammunition expenditure of 2 to 3 torpedoes per American merchant ship. This represented strategic victory for Thompson's engineering philosophy. His redundant systems had transformed Liberty ships from vulnerable targets into expensive objectives that consumed German resources disproportionately. Every additional torpedo a U-boat fired at a Liberty ship was one less torpedo available for other targets. Every hour spent pursuing a damaged but still operational freighter was an hour of exposure to destroyer counterattack. The Battle of the Atlantics, mathematics shifted decisively in Allied favor during 1943. German submarines sank fewer merchant ships per patrol, while Allied shipyards delivered Liberty vessels faster than the Kriegsmarine could destroy them. Thompson's redundancy was a major factor in this strategic reversal, though few people outside maritime engineering circles understood his contribution. The most dramatic vindication of Thompson's design philosophy came on November 9, 1943, when the SS Richard Montgomery took 3 torpedo hits from U-boat 515 during a convoy battle 300 miles west of Ireland. The first torpedo struck the bow, destroying number 1 and number 2 holds. The second hit amidships, breaching number 4 hold and flooding the midship cargo spaces. The third torpedo struck the stern, damaging the propeller shaft and flooding the aft engineering spaces. By conventional maritime engineering standards, the Montgomery was finished. 3 torpedo hits should have sent her to the bottom within 15 minutes. But Chief Engineer Thomas Bradford discovered that Thompson's redundant systems had created a ship that refused to die. The centerline steam line was severed, but the portside backup maintained pressure. The main generator was flooded, but the auxiliary generator came online automatically. The hydraulic steering was destroyed, but manual controls remained functional. Bradford coordinated with Captain Andrew Morrison to assess their situation. 3 compartments, flooding. Main propulsion available at 60% capacity. Steering operational via manual systems. Emergency pumps running on auxiliary power. We can make port if we move now. For 31 hours, the Montgomery limped toward Halifax at reduced speed, her crew manning pumps continuously, while destroyers provided anti-submarine protection. The ship arrived with 3 compartments completely flooded, her stern riding so low that following seas washed over the aft deck. But her engines still turned, her pumps still ran, and her crew walked down the gangway alive because Joseph Thompson had insisted on redundant systems that conventional wisdom called wasteful. Naval architects who examined the Montgomery's damage in Halifax dry dock found themselves confronting the physical evidence of what redundancy meant in practice. The torpedo damage should have been instantly fatal. Instead, the ship's distributed systems had maintained enough functionality to allow survival. The backup steam line had done its job. The auxiliary generator had provided power when the main unit flooded. The manual steering had maintained directional control after hydraulic systems failed. Captain Morrison submitted a detailed after-action report that Maritime Commission engineers studied intensively. His conclusions validated Thompson's engineering philosophy completely. This vessel survived circumstances that would destroy any standard merchant ship. The redundant systems provided time, options, and capability when everything else was failing. Every backup system earned its weight in steel, and then some. The Montgomery returned to service after 3 months of repairs, her battle-damaged compartments rebuilt, and her redundant systems meticulously restored. She completed 17 more convoy runs before the war ended, carrying over 100,000 tons of war materiel to European and Pacific theatres. The ship that should have died in November 1943 became a floating monument to Thompson's insistence that redundancy wasn't waste but wisdom. Thompson received a terse commendation from the Maritime Commission in January 1944, acknowledging his contributions to Liberty ship design. The official citation mentioned improved survivability characteristics, but provided no specific details about redundant systems or their operational impact. Thompson filed the commendation without ceremony, knowing that his true recognition came from casualty reports documenting what hadn't happened, ships that didn't sink, crews who survived, strategic cargo that reached its destination despite German attempts to destroy it. The negative space of prevented disasters represented Thompson's legacy, even if public recognition would never materialize. By spring 1944, statistical analysis confirmed what operational experience had demonstrated repeatedly. Liberty ships with Thompson's redundant systems survived torpedo hits at rates 3 times higher than comparable merchant vessels lacking backup systems. Of 296 Liberty ships that took torpedo damage during the war, 96 remained afloat and completed their missions after repairs. That 33% survival rate represented revolutionary improvement over the 8% survival rate documented for standard merchant vessels during early war years. Thompson's redundancy had transformed the mathematics of maritime warfare, creating vessels that gave their crews fighting chances rather than death sentences when torpedoes struck. The industrial achievement of implementing redundancy across mass-produced vessels impressed even skeptical observers. Britain's Ministry of War Transport sent engineering teams to study Liberty ship design during 1944, specifically examining how American yards maintained quality while incorporating complex backup systems into assembly line production. The British engineers returned with detailed reports recommending that future merchant vessel designs incorporate similar redundancy principles. Their assessment noted that American emergency cargo vessels displayed survivability characteristics that exceeded purpose-built British merchant ships, costing significantly more and requiring longer construction times. Thompson's philosophy had proven that redundancy and mass production were not incompatible opposites, but complementary aspects of effective compulsion, wartime engineering. The key was treating backup systems not as optional extras, but as fundamental requirements that deserved the same quality attention as primary systems. The Pacific Theater provided additional validation of Liberty ship redundancy under different operational conditions. Japanese submarine and air attacks created different damage patterns than German torpedoes, but Thompson's distributed systems proved equally effective at maintaining ship functionality despite battle damage. The SS John Burke, operating in the Southwest Pacific during 1944, survived a kamikaze aircraft strike that would have destroyed a conventional merchant vessel. The Japanese aircraft penetrated the forward cargo hold before exploding, creating massive structural damage and immediate fires. But the compartmentalization contained the explosion damage, while backup systems maintained power for firefighting equipment. Chief Engineer David Patterson kept emergency pumps running while damage control parties fought the fire for 4 hours before finally containing it. The Burke completed emergency repairs at Manus Island and returned to cargo service within 6 weeks, demonstrating that Thompson's redundancy addressed more than just torpedo vulnerability. The strategic impact of Liberty ship redundancy became mathematically undeniable by mid-1944. Commander Edward Simpson at the Navy's Anti-Submarine Warfare Operations Research Group conducted comprehensive analysis, revealing that Liberty ships comprised 41% of Atlantic convoy tonnage, but represented only 27% of ships lost to submarine attack. The redundant systems were saving ships at rates 3 times higher than conventional merchant vessels. German U-boat commanders recorded growing frustration in war diaries. Kapitänleutnant Heinrich Müller, commanding U-boat 953, wrote in November 1944, "Attacked American freighter in convoy. First, torpedo struck amidships. Vessel slowed but maintained power and steering. Second torpedo struck forward. Vessel still operational with destroyer escort closing. These American ships refused to die properly." The post-war analysis told the complete story. Of 2,710 Liberty ships built, 200 were sunk by enemy action. But 96 ships survived torpedo or bomb damage that would have destroyed conventional merchant vessels. Those 96 survivors represented over 320,000 tons of preserved shipping capacity and approximately 12,000 merchant mariners who lived because redundant systems gave their ships fighting chances. Thompson received formal recognition from the Maritime Commission in June 1945. Admiral Land personally presented a commendation, acknowledging his contributions. "Your insistence on redundancy seemed wasteful to many people in 1941, Land acknowledged. "But the operational data proves you were absolutely correct. Every backup system you specified has paid for itself many times over in saved ships, saved lives, and strategic capability." Thompson accepted with characteristic modesty. "I simply designed ships for the reality of naval warfare rather than idealized conditions that peacetime engineering assumes." Redundancy isn't complicated philosophy. It's acknowledging that things will fail and planning accordingly. The final statistics validated Thompson's engineering philosophy completely. Each Liberty ship cost approximately $2 million to build. Thompson's redundancy added $12,000, a 0.6% increase. The 96 ships that survived due to redundant systems represented $200 million in preserved assets, a return on investment exceeding 16,000%. But financial calculations missed the fundamental point. He had changed how engineers thought about failure itself. The SS, Jeremiah O'Brien, one of 2 surviving operational Liberty ships, became a floating museum in San Francisco. Visitors touring the engine room could see the triple steam lines, dual generators, and compartmentalized spaces that made Liberty ships notorious for refusing to sink. The O'Brien participated in 50th anniversary commemorations of D-Day during 1994, steaming across the Atlantic under her own power. The 70-year-old vessel completed the voyage without major problems, demonstrating that Thompson's philosophy created not just survivability but long-term durability. Thompson died in 1981 at age 87. His obituary mentioned his role in emergency shipbuilding, but provided no details about the survival statistics that validated his work. The recognition he never sought during life remained elusive in death. But among maritime engineers who studied ship survivability, Thompson's name carried weight disproportionate to his public profile. Modern maritime engineering continues grappling with tensions between efficiency and redundancy that Thompson navigated during wartime. The cruise ship Costa Concordia disaster in 2012 revealed how lack of adequate redundancy transformed minor accidents into catastrophic failures, contributing to 32 deaths that might have been prevented with more robust backup systems. The Liberty ship legacy extends into modern naval architecture through fundamental principles Thompson helped establish. Contemporary ship design standards require redundancy in propulsion, power generation, steering, and communications. These requirements trace directly to World War II experience, where backup systems proved decisive for survival. Thompson's story represents the quiet heroism of engineers who make decisions during peacetime that save lives during wartime. He never fired a weapon, never commanded troops, never engaged enemies directly. His battlefield was the drafting table where he made choices about steam piping routes and generator placement, decisions that seemed mundane but ultimately determined whether sailors lived or died in the North Atlantic. The courage to insist on redundancy despite institutional resistance, to add cost and complexity when efficiency was demanded, to design for failure rather than optimizing for success, these represented moral choices as much as technical decisions. Thompson chose to prioritize lives over construction efficiency, to value survival over marginal performance improvements, to accept criticism for engineering that seemed wasteful until the torpedoes started hitting. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.